SwayamPrabha. Digital India. Educated India.
Lecture in this lecture series for modeling of multiphysics system. In today's lecture we will move on from thermal transport or heat transfer to mass transfer. Mass transport or mass transfer is a continuation in the domain of transport phenomena, which includes both heat and mass transfer. There is a similarity between what we have studied during heat transfer and it can be directly related to mass transfer. Okay, so in heat transfer what we had studied is that a temperature difference would cause the thermal energy to propagate. In a better perspective, it was a gradient of temperature. Likewise, in mass transfer, it is either the concentration or the density of the species, that is the difference in the mass or concentration that causes the species to go from one segment to another or from one section to another. So, the gradient in concentration or concentration difference of a species in a mixture of species causes mass transfer or mass transfer to happen, right. So, both of them are a part of the global ensemble that we called the transport phenomena, right. So, heat and mass would be taken likewise. The relations are similar, both of them are diffusion based or convection based phenomena. And they are treated by more or less a similar set of formulation. So, we can quote this. So, mass transfer is mass in transit as the result or as a result of a species concentration difference in a mixture. Okay, so, this is by definition. So, mass transfer is that the mass is being transit or moves because one species has a larger concentration at one segment and has a lower concentration in another segment. So, in this case this is the driving force, this concentration difference, just like the temperature gradient or temperature difference was a driving force in the case of heat transfer. Okay. So, again like heat transfer we can have two kinds of mass transfer. So, one is conductive mass transfer, conductive in this case is called diffusive mass transfer. Right. So, it was conductive heat transfer, which is equivalent or equals to the diffusive mass transfer, and then we have convective mass transfer. So, two modes by which mass can be transported. One is diffusion. Diffusion means that the overall the bulk velocity is ignored. There is no net motion of the species, it is in stagnation, and then due to the concentration difference, although species will move, right, it is mass is being diffused from one end to another end. For example, in this diagram over here. So, species A has a larger concentration at this end and species B has a larger concentration on this end. We have a partition in which initially all this on the left hand side was all species A and right hand side was all species B. Now, as you would remove this partition, the species B would move from right to left because right has a larger concentration of B and left has almost no B, and species A would move from left to right, again left side has a larger concentration of A compared to the right hand side. Therefore, the concentration of A would gradually move from this left hand side to this right hand side, and concentration of B would move from the right hand side to the left hand side. This will continue till both the profiles have equilibrated, and this kind of motion also there is some velocity in for the particles, right. Of course, how would the A go towards the right hand side and B go to the left hand side, but the net motion of the ensemble of the bulk is stagnant, and that is the example of a diffusion based mass transfer, right. Compared to this, if you look at convection based mass transfer, then the bulk also has a velocity. So, it is a combination of diffusion and advection, right. So, just like heat transfer, in which there is a fluid moving on the surface, say wind is flowing and temperature or the heat is being transferred. So, a hot surface gets cooled down because the heat is being transferred by the moving fluid away. In the same way, you can have a surface of fluid and another fluid is flowing, say water is there, and another fluid, say air, is flowing on top of it. This air has a lower concentration of water compared to this liquid pool. So, the water will evaporate into the air and will go away. This is called convective base or convection mass transfer. Right. We do not have the third mode of heat transfer equivalent for mass transfer. Radiative heat transfer is motion of electromagnetic radiations through space. It does not need a medium. If there is a medium, it is affected by the refractive index of that medium. However, in the case of mass transfer, a species itself will not exist if there is vacuum, right. If you remove all species, then what will diffuse? Nothing is there to diffuse. So, there is no radiative mass transfer, there is only diffusive mass transfer and convective mass transfer. Okay. So, in diffusive mass transfer, as we said, bulk motion of mixture is ignored. So, we are ignoring the bulk motion of this, and only the flux of A through the flux of B is considered, or through this ensemble is considered. Okay. So, with this we have now have some idea of what mass transfer is. It is not taught in that detail typically in an undergraduate level. It is an important concept, just like heat transfer. It has several differences from heat transfer. It is actually something that is moving, unlike heat, which is an energy or a wave that is being transmitted. In the case of mass, it is not an actual wave, right. It is the species itself that is moving back and forth, not just the vibration of the species going forward or backward. So, there are limitations, right, and boundary conditions have different meanings depending on heat is one effect itself. Mass needs to be between two species. So, if there is just species A and there is no species B in that bulk, then the concentration is uniform everyone. Only when another species is introduced or we have a multi-species system, only then mass can be transferred. So, these are certain differences between heat and mass transfer, which takes us to the segment of mixture fractions, right. So, if you have a mixture of gases or a mixture of solutions in which different species exist, then we can find out what are the equivalent densities and concentration. So, a mixture consists of two or more species which are chemicals. The density and concentration of the species are relatable. How are they relatable? So, they are relatable by the molecular weight. So, rho I is the species density of the ith species, mw is the molecular weight of the ith species, and Ci is the concentration of the ith species. So, this is density, the unit is kg per meter cube, this is molecular weight, the unit is kg per kilomole, and this is the concentration, all for the ith species, kilomole per meter cube. Okay. So, that is how you can convert concentration to density and vice versa, right. So, they are linearly dependent on each other, and molecular weight is a constant for that species. So, the mixture density or concentration is a superposition of all the species, which means that rho is equals to summation over I rho I, and C is equals to summation over I C I. So, we are adding all the concentrations, and that gives us a net concentration of the bulk, and summation of all the densities will give us a net density. Okay. From here we can find out that if we divide rho throughout this and C throughout this, we get the mole fractions and mass fraction. So, the mass and mole fraction are, so Xi is our mole fraction, is Ci over C, and say Yi is our mass fraction, is rho I over rho, okay. By property, since C is equals to summation over I C I, we can say that summation over I of Xi is equals to 1, and summation over I Yi is also equals to 1. Okay. So, summation of all the species mole fractions is 1, and summation of all the species mass fraction is equals to 1. This is the general rule, and this applies for all chemical mixtures. Now, for an ideal gas, for a gaseous mixture, considering ideal gas, behavior, we know by ideal gas that PV is equals to n R bar T, where P is the pressure, V is the volume, N is the number of moles, R bar is the universal gas constant, and T is the temperature. Okay. If we take V to the left hand side, then Pi is equals to Ni over V at a constant volume, R bar into T. This Ni over V is Ci, is a concentration, R bar into T. Okay. So, P, which is a total pressure, is summation over I Pi is equals to summation over I Ci, R bar into T equals to C R bar into T. All right. So, we can find out this relation, and that is the Dalton's law of partial pressure. Which suggests that the summation of all the partial pressures is equal to the total pressure of a system. So, if I have say 2 moles of hydrogen and 2 moles of oxygen in a system that is at 1 bar pressure, then the pressure for hydrogen will be 0.5 bar and pressure for oxygen will also be 0.5 bar. Likewise, PV is also equals to m R bar by molecular weight into T is equals to m R T. Right. So, for the ith species, Pi is equals to m I over V R I into T, which is equals to rho I R I into T. So, again summation over I Pi is equals to P, and summation over I rho I is equals to rho. Okay. So, same relations can be derived from this. Now, we have an understanding that we need to have at least a binary mixture for mass transfer to happen. It can have in multi-component diffusion as well. You can have several species, several gases, several liquids mixed together. In many cases, you could have chemical reactions happening in which one species is converting to another species, and that is where these models are being developed. You are able to account for how much mass is getting consumed and how much mass is getting generated. So, Fick's law or mass diffusion is based upon the concept of conservation of mass. So, let us write that that mass diffusion Okay. We will come to the conservation of mass part, let us underline this. Just like heat transfer was based upon conservation of energy, we will do a similar derivation for mass transfer. Before that, let us see what Fick's law states. So, the Fick's law or the Fick's first law for diffusion, it states that the mass flux or the mole flux for an ith species is equals to the diffusion coefficient times the gradient of the density if it is mass flux for the mole flux, the gradient of the concentration for the ith species. So, this is our mass flux, the unit is kg per meter square second, and this is our mole flux, kilomole per meter square second. Okay. This is very similar to our conduction equation. If you remember our conduction heat conduction equation, our heat conduction was Q, that is our heat flux, was equals to minus K del T, right, where K was our thermal conductivity and del T was our temperature gradient. In the same way, the mass flux, the concentration flux or mass flux, it is equals to the negative of the diffusivity, that is the mass diffusivity, of species A in species B times the gradient of the concentration or gradient of the density. So, the concentration and density are the driving parameters or the driving forces, and this results in the flux of A through B or B through A. We will see how the other direction is also relevant. Okay. This DAB, this diffusivity in gases is proportional to the pressure to the power of inverse 1 and temperature to the power of 3 by 2, and this comes from the kinetic theory of gases, considering ideal gas behavior. Right. The diffusivity in the case of liquid based solutions are much more complex. Typically, it is hard to derive a single formulation for diffusivity. We usually use the concepts of molecular diffusion and particle to particle interaction and collision in the case of solutions, right. So, there are many other parameters which come in, whether the particles can have zeta potential, can be interacting with each other. There are empirical relations which can give you diffusivity, and experiments are used to measure these. But in theory, it is difficult to have a single formulation defining diffusivity in the case of solutions. In the case of gases, it is easy, and we can use this pressure temperature relation for this case. Okay. Now, the Fick's second law, it is used to derive our diffusion transport equation. Okay, so, the mass diffusion equation or the mass diffusion transport equation. We start with the same analysis as that consider an arbitrary volume bound by a piecewise continuous surface, same expression as last time in heat transfer. Okay. So, we have this arbitrary volume V, and it has this piecewise bounded by a piecewise continuous. It does not have to be smoothly continuous. It can be a rectangle, it can be a cube, it has sharp edges. So, piecewise continuous, but it needs to be continuous. There should not be any discontinuity or opening, right, a surface. In that case, let us draw arbitrary volume again. Okay. The net mass stored in the volume is equals to the net mass influx through the surface. Okay. So, the rate at which mass is getting accumulated in this volume V is equals to the rate at which mass is getting into the system, and this makes sense, that is a conservation of mass, right. So, if that holds, then by conservation of mass, our dm by dt storage is an integral over volume del rho by del t into dV, and dm by dt for our influx, and I am emphasizing influx because we will put a negative sign, del V, our flux of the given species. For example, we are doing species A, let us put in A over here. So, J A vector dot with surface normal into ds. Okay. So, surface normal is always outwards. So, if this surface is bound, you will have the surface normal always outwards. Influx, the dot product needs to be negative to determine influx. Okay. Now, we relate these two. So, according to the conservation of mass, so COM, we will have integral over volume V del rho A by del T dV is equals to minus integral over the surface S J A dot with surface normal n cap into ds. All right. We can bring to the left hand side. So, integral over volume V del rho A by del T dV plus integral over volume surface S J A dot with surface normal ds is equals to 0. So, this is our conservation equation. It looks very similar to our heat conservation equation, right. We had del rho V rho Cp del T by del T, and against that we have this basis. So, we can then proceed to the next step, that is the use of Gauss divergence theorem. And converting this surface integral to a volume integral. Okay. And then we can substitute this back into our equation. We can combine all the volume integrals into one. Okay. Now, again comes our question that for an arbitrary volume, the integrand needs to be 0. So, why is that? If I would again explain, just like heat transfer, we had that for this volume, we can have this term inside this integration. Say either this can be say plus 1, this can be minus 1, this can be plus 3, this can be minus 3. The summation of all of them will be 0. That is one thing to happen, that the net integration. But then if this is an arbitrary volume, then these smaller volumes are also arbitrary volumes, right. But then this integration or the term inside the integration or integrand should also hold true for those smaller volumes as well. That is why these are incorrect, and at every place it should be 0. Right. So, if that is the case, then this del rho A by del T plus del dot J A is equals to 0. This is our mass diffusion equation. Okay. We can then substitute J A from Fick's law as minus d A B del of rho A, and we get del rho A by del T, taking this to the right hand side as del of dAB So, DAB in this case is a mass diffusivity. Mass diffusivity is not a constant, it is it's a tensor quantity. It converts our gradient of density to our mass flux or the change of the concentration or the density. In terms of density, this is del Ca by del T is equals to divergence DAB of gradient of concentration. Okay, same formulation, same equation. We just replace rho by C. DAB is the same, mass diffusivity for molar basis is same as mass diffusivity for mass basis, right. Okay. Now, dimension analysis. So, let us again rewrite our mass diffusion equation. Say for a 1D body, let us draw a 1D body. Say in this case we are diffusing species A, in a uniform B. Okay. Say the left hand side has a concentration of species as Ca 0 and the right hand side can have some convection out, say Hm into Ca infinity. All right. So, our mass diffusion equation del Ca by del T will be equals to DAB, if DAB is isotropic and homogeneous, del square Ca. We will need two boundary conditions and one initial condition. So, our initial condition will be Ca at x comma time 0 will be say Ca 0. Now, a boundary condition is or R in this case is that Ca at 0 comma t is equals to Ca 0 and minus d del Ca by del x at L comma t. Say this is x is equals to 0 and x is equals to L is equals to Hm, just like a convective heat transfer we can have convective mass transfer out. So, Ca at L comma t minus Ca infinity. So, this is a Dirichlet condition, this is a Robin condition. We can also have some some J star of A at this end, this becomes a Neumann condition. So, if you know a fixed flux, then we can also put a J star of A, that becomes a Neumann condition, that is also valid. So, three types of condition can exist. Can anyone tell me or can you guess what would be an impermeable wall? Say I have mass transfer from here to here onto this surface, this is a wall and nothing can go beyond this wall, then this becomes an impermeable surface. Impermeable means that the net flux will be 0. Its equivalent in heat transfer is an adiabatic wall, right. Okay. So, with these let us normalize our equation. So, if we normalize our equation, so let us take C bar of A is equals to Ca minus Ca infinity over Ca naught minus Ca infinity. Let us take x bar equals to x over L and let us take T bar equals to T over some T naught. Okay. Substituting these just like we did for heat transfer back in equation, our governing equation will be Ca naught minus Ca infinity divided by T naught del Ca bar by del T bar is to DAB Ca naught minus Ca infinity divided by L square del square Ca bar by del x bar square. Okay. These terms get cancelled. We can take everything to the left and that is our we can clear out our highest order derivative. So, L square over T naught into DAB del Ca bar by del T bar will be equals to del square Ca bar by del x bar square. This term can be made 1 if T naught is equals to L square over DAB this is our diffusion time constant. If you recall from heat transfer, T naught for thermal transport or heat transfer was L square over alpha, where alpha was our thermal diffusivity. Thermal diffusivity, mass diffusivity have the same units, meter square over second. However, this L square over dAB and L square over alpha may have different values, right. For example, alpha can be in the range of 10 to the power of minus 4 or 5 for L equals to 1. That means our or L can be in millimeters. So, in that case our thermal time constant can be in say L is in the range of, L is approximately 10 to the power of minus 2, alpha is approximately 10 to the power of minus 4, and say D is in the order of 10 to the power of minus 8. Right, we have very poor diffusivity, we have a slightly higher thermal conductivity. So, time constant for the thermal counterpart is in the order of 1 in seconds, and time constant for the mass transfer, the heat transfer, for the mass transfer will be in the order of 10 to the power of minus 4 by 10 to the power of minus 8, that is 10 to the power of 4 seconds. So, in such a case we can see that the heat equation can equilibrate very quickly, mass equation does not equilibrate that quickly or does not come to a steady state that quickly, which means that if we are solving a coupled problem of both heat transfer and mass transfer, in that case heat transfer equation can be considered steady state for every time step of mass transfer, right, because heat transfer converges very fast. So, this is how we can simplify a coupled equation. When we come to coupled equation and when we solve for both heat and mass transfer problems together, say some chemical reaction or say convection, natural convection or forced convection, in that case we can make approximations of steady state for heat transfer or for mass transfer. Okay. One more thing before we go to the next segment is that if you look at our boundary conditions, let's quickly go over our boundary conditions. So, we have our Ca at 0 comma T bar will be equals to 1, and our del Ca bar by del x bar at 1 comma T bar will be equals to a Biot number for mass transfer into Ca bar. You try this out, this will be same as heat transfer, but this Biot number thing is Hm. You just substitute over here is Hm over D into L. Okay, slightly different from heat based Biot numbers, but it is HML over DAB. Okay. Now, we are going towards a slightly more complex directions. So far we have assumed that the media was stagnant or stationary, it was not moving, there was no bulk velocity in the media. Now, let us start introducing some concepts of bulk velocity, right. So, if you do have bulk velocity, then our net flux should be a summation. So, the net flux, the summation of our diffusive flux and our convective flux. So, our net flux should be in some order will be equals to d del C plus C into V, okay, where C is the concentration. So, d del C is the concentration gradient, that is our diffusive flux, and C V is where V is a bulk velocity. So, it is our bulk concentration flux. Okay. Let us start with this. The absolute mass flux is a superposition of this diffusive and advective mass fluxes. So, in a binary mixture, of A and B, let species A have an absolute velocity V A. In this case, the net flux of A is N A will be equals to rho A into V A. Let us put a so N A is a net flux, that is density of A into the absolute velocity of A. What is absolute velocity? It is that if the bulk is also moving and the species itself is also moving, in that case it is a summation of the bulk velocity and the species velocity, right. So, the entire thing how it moves, how the particle A moves, right. There can be a situation in which there is no diffusion, but the bulk itself is moving, say air is flowing, right, but there is no mass transfer, it is a homogeneous mixture, right. In that case we will just have bulk motion. So, we are just looking at the species A in a control volume, and we are seeing how that species is moving, and that will be our total flux of the species A, right. Likewise for B, so this is our average velocity of A in a small CV, a small control volume. N B will be equals to rho B V B. Okay. The mean velocity, so we can find rho V equals to rho A V A. So, the rho B V B, this is the net momentum that we are adding up, mass into velocity. So, rho V equals to rho A V, and so V will be equals to Y A into V A plus Y B into V B. We know that rho A over rho is Y A, that is a mass fraction of A, and Y B is a mass fraction of B. Okay. So, that is the net or mean velocity of the bulk, how the entire thing is moving back and forth, not just the species A and species B. So, the relative flux of species A, we can find this as J A, that is what we have been using earlier. J A vector equals to rho A V A minus V. Okay, let us put vectors everywhere. We should write this in vectorial terms. These are vectors. This is vector. This is vector. Okay, should not miss the vectorial signs. Density is a scalar, right? Velocities are vectors. All right. So, if this is the case, we can expand this as rho A V A bar minus rho A V bar. Rho A V bar is something we find it based on mean velocity. This is our N A bar. So, N A, the net flux, is J A plus rho A into V. Okay. We can substitute J A over here, and N A therefore is equals to minus D A B del rho A plus rho A into V vector. So, V is ensemble velocity, and that is what we have written earlier, and that is where we started with. We have our diffusive component, we have our advective component. So, again our diffusive component over here and our advective component over here. Now, we can substitute back V over here. So, V was equals to Y A into V A plus Y B into V B. So, N A is minus D A B okay. So, that becomes our net flux or the net species flux. We can then make certain modifications inside this. We can take our rho A inside, so rho A into Y A, rho B into Y B, and make certain changes to make this equation some linear reorientation del rho A is Y A. So, multiply with rho, so multiply divided with rho, rho into Y A is rho A into V A plus rho B into V B, and if we look back, N was rho A V A, N B was rho B V B. So, we can write this or rewrite this equation minus D A B del of rho A plus fraction N A plus N B. So, we can find out N A in terms of N B and likewise for N B in terms of N A, right. Likewise N B minus d B A del rho B N B. Okay. So, one outcome that we can get out from here, that if J B equals to 0, there is a net flux is 0, also x y B equals to 1, then the gradient of y A minus gradient of I B. If you multiply density to both sides, then the gradient of rho A will be equals to minus gradient of rho B. Okay. Now, if you compare both of these, so if we have J B is equals to minus J, J B is d B A del of rho B, minus sign, minus of minus d A B del of rho A. Okay. So, we can say that d B A is equals to d A B, and that is true for any binary species. The diffusivity of A in B is same as the diffusivity of B in A. So, we can substitute these back and forth into each other. All right. If this is clear, then we will move into some examples. We will take two examples. One is for an evaporative based cooling and one is for a chemical reaction based. Okay. So, for the evaporative cooling, you consider a tube containing liquid species A, air containing A plus B is a mixture of the binary mixture of two species, flows over the tube such that the top surface has a fixed concentration right, the fixed concentration of XAL. The gas is at a constant pressure. All right. At the liquid surface, the concentration of species A is X0. All right. X is again mole fraction. We can interchange between mass fractions and mole fractions very easily. So, let us write this. This is X is equals to 0 and this is X is equals to L. At the surface, our X concentration is XA0. At the top, our X concentration for A is XAL. We are having a flux going from the bottom of this liquid, that is because XAA. So, then XA0 is greater than XAL, because this is saturated liquid just at the surface, just evaporating, and the fluid at the top is not having that much concentration of A. So, A will diffuse from XA0 to XAL. Okay. So, it will diffuse from x equals to 0 to x is equals to L. At steady state, we can assume that the net change in flux of A, the mole flux of A is 0. Right, this comes from our, if we quickly go back to our mass conservation. So, this was our Na x, right. So, and if we take it in one dimension, then del d n a by dx or del n a by del x equals to del c a by del t, and the steady state this term is 0, this left hand side term becomes 0. So, in that case we will have d n a x by dx equals to 0. Okay. Up to this it is correct, or it is fine. Our total concentration is C a plus C b, which means that x a plus x b is equals to 1 everywhere. This holds. Also x b of L is greater than x b of 0. So, we have a larger concentration of species B at the surface, while B is smaller inside. We also assume that B cannot diffuse in A. So, the species B cannot diffuse in the liquid state, it needs to be in the gaseous state, and that means that there is no velocity, it is not getting consumed anyhow. So, at equilibrium we can say that n b of x is equals to 0. Why is this 0? Why is the net flux 0? Because A is evaporating, so A is getting out from liquid to vapor and is being carried away by the binary mixture outside, but B cannot diffuse into A. So, there is no way for B to go, and at steady state the net flux becomes 0. So, B flux is 0, so stagnant. Okay. That does not mean that B has a gradient and does not have a gradient. B does have a gradient, but is a constant, the gradient is equals to 0, concentrations are still there. So, we know that N A x is equals to minus d A b into concentration, total concentration del x A plus x A N x. Okay. We can rearrange the terms and we can say N A x is minus C into d A b 1 minus x A d x A by d x. Okay. So, we are solving for this equation, we have this n value, substitute n d n A by dx equals to 0. We get d by dx minus c d A b 1 minus x A dx A by dx to 0. Okay. Or since c and d A b are constants, they can go out, we will have d by dx 1 by 1 minus x A dx A by dx is equals to 0. So, if you solve this equation, you will get minus natural log of 1 minus x A to C 1 x plus C 2. What do we have? We need two boundary conditions. So, at the top boundary L, you have a concentration as C A L. At the bottom boundary, you have a concentration of C A 0. So, if you substitute these, we will have 1 minus x A over 1 minus x A 0 is equals to 1 minus x A L as x A 0 x over L. So, this becomes our solution. Now, since x of b is equals to 1 minus x of a, you can say x b over x b 0 is equals to x b x over L. Okay. Right, and we can also get our flux. So, the flux N A of x, we can find this out as C d A b, C into d A b rather, over L. If you take a derivative, natural log 1 minus x A L, this is at the surface, at the top surface. Okay. So, this becomes our net flux. for our given species. So you understood how this species would evolve and how it will be given out. Your net flux for the B is stagnated. We have species A evaporating from this liquid and is going out into the binary solution, and this is given by this natural log base term. The last example that we will try out today is a reaction diffusion based problem. So, reaction diffusion is that you have this container where species A is getting consumed, we have an impermeable boundary. So, the top surface has a constant concentration of Ca0 and bottom wall is impermeable, which means that minus d del C by del x at x is equals to L equals to 0. Okay. So, it is an impermeable wall at the bottom. That is the case, our mass transfer equation del Ca by del T will be equals to dAb del square Ca by del x square plus some mass generation term, just like a heat generation term. So, this is our source if it is positive or sink if it is negative. Okay. Under steady state, dCA by dt is equals to 0 equals to dAb del square Ca by del x square plus n dot A. Now, what is n dot A and how do we find it? It based upon the kinetics of the reaction. For a 0th order kinetic model, n dot A equals to k 0. For let us go back one slide. For a first order kinetic model, n dot A equals to k 1 into C A. For a second order model, this will be dependent on C A and some other species and so on, right, or C A square and so on. So, it just goes by the power. So, assume a second order, a first order consumption. We will have dAb of d square Ca by dx square minus k 1 of Ca is equals to 0. This is our equation to be solved. In this case, if we look at the solution, so this is a second order ODE. The solution for Ca as a function of x will be equals to some constant C1 exponential of mx plus C2 exponential of minus mx, right, where m in this case equals to our k 1 divided by dAb square root of this. Okay. So, if that is the case, then we can find out based upon our initial and boundary conditions. So, sorry, based on boundary conditions. So, boundary conditions were that Ca at 0 is equals to Ca 0 and minus dAb del Ca by del x at x is equals to L equals to 0. Substitute these boundary conditions. Let us go back one slide. Let us write it over here. So, substituting our boundary conditions, we will get the solution for Ca, and the Ca will come out, Ca of x will be equals to Ca 0 cos hyperbolic m of L minus x by cos hyperbolic m of L. This is the solution for this reaction diffusion type problem. We can find Ca at L, that is at the bottom wall, the concentration is Ca 0, cos hyperbolic of 1 will be 1 and we will just divide by cos hyperbolic, sorry, a cos hyperbolic of 0 is 1 of ml. Okay. So, this becomes our lower wall concentration, and our flux at top surface. So, we can find it out, N A of x equals to minus d A B d C A by d x. So, we can find this N A at 0 will be equals to d A B C A 0 tan hyperbolic of ml. Okay. So, these becomes our solution for a reaction diffusion problem. I will just go upon this multi-domain transport phenomena. So, multi-domain is that you would have multiple domains. Transport phenomena can either be heat transfer or mass transfer, in which you have some species diffusing from here to here and then some other species diffusing from here to here. In this case, one extra boundary condition is needed. Just let us talk about heat transfer for now to make it simple. Del T by del T equals to alpha del square T by del x square, say plus some q dot. Say this is for each domain. So, this is a domain 1, this is domain 2. So, this will be 1 comma 2, 1 comma 2 and 1 comma 2, right. So, you will have your boundary conditions here and here. At the interface you will also have a boundary condition, and that is minus k 1 del T by del x at x is equals to this interface x star negative equals to minus k 2 del T by del x at x is equals to x star positive. Okay. So, this additional boundary condition you need to solve at this interface apart from the two walls. With this you can actually solve multiple domains of condition. This is also applicable for mass transfer. When you have species, say in a battery, electrode ions are going from cathode to anodes, you have multiple domains and you can apply this concept in those domains. So, with that, let us wrap up our transport phenomena in this lecture. We have studied about heat transfer, mass transfer. Our analytical solutions and numerical solutions for heat transfer will directly apply to mass transfer, and you can solve them accordingly. So, you use the same models as taught in last class for the mass transfer and see if you can find a similarity. So, thank you for listening, and we will meet in the next lecture. Thank you.